International A level chemistry unit 5 for October 2021. I will begin with section A. So let's go to the first question. This is basically 90 marks, as you guys already know. So the first question is about, of course, standard electrode potential. So it says the apparatus shown was used to measure the standard electrode potential for the reduction of dichromate ion to chromium 3 ion in an acidic solution. So they gave you the electrode potential, basically the equation for the half equation for the cell having the dichromate and chromium 3. So here we see this cell here has information concerning, of course, hydrogen gas. There is an electrode 1. Actually, I'm the one who wrote this here. So, but I just showed you electrode 1, and then there is solution 1. Of course, you guys know if it's hydrogen gas coming in, let me get some highlighter here. If it's hydrogen gas coming in, and this is a half cell using the standard hydrogen electrode, it means the electrode we're going to use here is going to be platinum, and the solution has to be 1 mole per decimeter cubed of an acidic solution. In this case, usually it's hydrochloric acid. The other half cell, as we can see here, they've also given us there is solution 2, electrode 2. However, since the question told us there is dichromate chromium 3 half cell, it means this is the dichromate chromium 3 half cell. It means here we have a solution, a mixture of basically 1 mole per decimeter cube dichromate and 1 mole per decimeter cube chromium 3. And then we also have an electrode which is going to be made of platinum. The reason as to why this electrode should be made up of platinum is we have 2 ions in solution that are made out of the same metal basically. You cannot use that metal again as an electrode because it's going to bring about reactions that were not required in this specific half cell. So let us continue down here to the questions. Okay, let me erase this as well. Okay, so the first question says, which material should be used for the electrode? Of course, like we already said, this is a standard hydrogen electrode, basically with hydrogen gas. The electrode here should be platinum as well. The electrode here should be platinum again because there are 2 solutions of ions. There is a mixture of solution of ions made up of the same metal. So platinum and platinum on both half cells. Let's go to the next question, which is question 1b. They say solution 1 is, again, solution 1 is basically the solution in the hydrogen gas half cell. So, of course, it should be 1 mole per decimeter cubed. Hydrochloric acid, we need 1 mole per decimeter cubed monobasic acid because we can guarantee that this is going to give us the concentration we want. If you are using 0.5 mole per decimeter cubed of hydrogen, you cannot guarantee that all these hydrogens are going to be released to give you the exact concentration you're looking for. So this is going to be the best answer here, a monobasic acid in this situation. The others will not be giving us the right concentration we're looking for. Okay, or the right number of moles in that specific solution. So we go to the next part. Solution 2 contains 14.71 grams of potassium dichromate. This is solution 2 in the dichromate chromium 3 half cell. Then they ask what mass of Cr, or of course this is chromium 3 sulfate. They give you the number of moles of water should be used in here. This is kind of a tricky question for some students, so I did my explanation down there below. But all we need to know is you need to know the equation for the reaction. So I want to show you down here where I wrote my full explanation. The key thing to understand is this equation here for the reaction of this specific half cell. Chromium, dichromate reacting to produce chromium 3. Of course, 1 mole of dichromate produces 2 moles of chromium 3. That is the half equation. So if we want to find out how the number of moles of the how much chromium 3 sulfate should be used, we got to begin by finding out the number of moles of dichromate. So we know in 1 mole of potassium dichromate, of course, we have 1 mole of dichromate. You can see 1 mole of this whole thing contains 1 mole of that. So we can guarantee that 1 mole of dichromate, potassium dichromate contains 1 mole of dichromate, like you see here. So that means if we are trying to find the number of moles, we can say number of moles will be, of course, in this case, it's going to be, we're given the mass and the molar mass. From the question, the mass of potassium dichromate was given to us, which is this. So we will do that mass, divide by the molar mass of potassium dichromate in order to find the number of moles as 0.05 moles. So in that dichromate chromium 3 half cell, they're going to be 0.05 moles of dichromate. Now we're going to use this to estimate the number of moles of chromium sulfate. Of course, the number of moles of chromium sulfate that have to be added in the same solution to give us the exact, to give us similar concentration as this. When we go back to this, you can see chromium sulfate. Each mole of chromium sulfate actually has 2 moles of chromium 2. It means if we want the concentration of this and that to be the same, we have to use half. Basically the number of moles of chromium sulfate used should be half the number of moles of dichromate used if we want the same the concentration to be the same. Let me give an example by drawing something. If we have a solution, maybe 1 mole per decimeter cubed, and our final aim is to have exactly the same concentration of each, so we put in chromium 07, this is dichromate, and then we are supposed to put in chromium 3+. Now because this produces twice, we should add half of it in order to have 1 as similar to this. This just produces once, so add 1 instead of adding a half, so that in the end we have similar concentration of the 2. I don't know if that makes sense. That is what I try to explain here in words. Down here in words. So it means that if we want to get, because it's the same volume, they're all being added in the same volume. If it's 1 mole, if the volume is 1 mole and our final concentration we want is 1 mole per decimeter, if the volume is 1 decimeter cube and our final concentration should be 1 mole per decimeter cube, it means we need to add that the moles added here should be 1 mole and that should be 0.5 moles, since that the solution added, which is chromium sulfate, produces twice. If each is 0.5 mole, it means in here we will have 1 mole of that as well, and the concentration will be as required, meaning both of them will have the same concentration. I hope that makes sense. Let me put that down here because it's not to do with that question. You can just put it down here as an extra explanation. So let me go back to this question here. So this question, they say solution 2 is best acidified with. Now solution 2, of course, we are trying to, the dichromate chromium 3 is best acidified with sulfuric acid. This is because, of course, chloride ions will be easily oxidized, and that will actually affect the cell or affect the reaction going on. So it's better we use sulfuric acid. Let's go to the next question. Question 2. The equation for a redox reaction is as given. They say which is the correct cell diagram to measure the E theta for the cell for this reaction. If we want to be able to write or draw the correct cell diagram, we have to look at the equation to find out where oxidation is occurring and where reduction is occurring. So here we can see iron 2 is being converted to iron 3. It means that is oxidation. And the half cell where oxidation takes place is going to be inserted at the left side, while the manganate 7 converted to manganese plus 2, that is going to be reduction, so that is going to be to the right. So it means the cell diagram is going to be written from left to right. Since we have ions from the same metal in iron 2, as well as manganese 2, we have to use platinum electrodes in both half cells. So the electrode will appear first at the end. We position a line between the electrode and the ions. Since we have 2 ions, iron 2 and iron 3, we will write them right there, iron 2 plus, put a comma between the ions in the same solution, and iron 3 plus. Then remember, the most oxidized version of the ion is going to be closer to the salt bridge. Then we position the salt bridge like that. And then on the other side, we have to position the most oxidized version closer to the salt bridge. In this case, it's going to be MnO4 minus. However, here MnO4 minus is attached to H plus, so we put 8H plus, put concentration brackets, and put a comma because these are 2 fine ions of solution, and then put another concentration bracket between manganese 2 plus 4H2O, and then a line, and then platinum at the other side. Here the correct answer should actually be C. Let's go to the next part. They say some standard electrode potentials are shown. Here we see, they say, which of these disproportionation reactions is thermodynamically feasible? Now, if we want to see which reaction is going to be thermodynamically feasible, we need to know which reactions they are. The first one is from BK3 plus to 2 and 4. I'm going to use this equation as well as this equation. So we have that and that. We can see moving from there to there and moving from here to there. So it means this is going to be on that side and this on the other side. Now, if this is generating electrons, it's going to be on the left. This is going to be on the left side, and that is going to be on the right side. That means if you want to find the E theta for this cell, E theta for this cell is going to be the E right minus E left, which is negative 2.80 minus 1.67, which gives us a negative value, so it's not feasible. Next, we go to the copper half cell. Here we have that copper 2 to copper 1, and we have copper 2 to copper 3. So it's going to be these two. Again, because it's from copper 2, all are starting from copper 2, it means that it's going to go like that, and the other is going to go like that. I think I better use a different pen. So it means this is going to be using up the electrons, so it's going to be on the right, and this is going to be generating the electrons, is going to be on the left. The E theta for this cell is going to be the E right minus E left, so 0.15 minus 2.40, which is also negative. So this is out. Next, let's go to the gold one. Gold 1 to gold and gold 2. Okay, Au1 to gold, so we have that and that. So it means gold 1 to gold and gold 1 to gold 2. This is generating electrons, so this is on the left and that is on the right. So it means we're going to find the E theta for this cell will equal to, again for the gold, I'm going to say this is going to be right, which is 1.69 minus left, which is, let me see, 1.69 minus 1.8, 1.80. This is also negative, so it's not. Lastly, we have the silver one. Let me see, we have this and this. So this is going to the negative side, that is going to the positive. So negative, so in this case, because it's going to be reversed, this is going to be generating electrons, so this is to the left and this is to the right. So it means the E theta for this cell is going to be 1.98 minus 1.80, which is positive, and therefore it's feasible. Question 4, which is true of a hydrogen-oxygen fuel cell? The first one says a cathode has more positive potential than the anode. This is correct, actually. The cathode is where we see reduction is going to occur, as the anode is where oxidation is going to occur. So the anode is a negative electrode. If I try to expand this out for you, this is from your textbook. I think you can look at it and see. This is where we have the anode, which is the negative electrode, the anode, and the other side we have the cathode, which is the positive electrode. So we can see oxidation will occur here and reduction will occur the other side. I'm going to make it smaller and take it back where it was, and then I'll continue with the paper. So the answer here should be A. Question 5 says, which of the following statements best explains carbon monoxide poisoning? Carbon monoxide poisoning is brought about when carbon monoxide basically binds to hemoglobin, or to the iron basically in hemoglobin, than oxygen. Okay, the binding of carbon monoxide is going to be stronger than that of oxygen. So here, they say carbon monoxide binds irreversibly. Not necessarily. The reason as to why people have this or experience this carbon monoxide poisoning is the bond, or the dative covalent bond formed between the iron in hemoglobin and the carbon monoxide is stronger than that of oxygen. So B comes out to be the correct answer. Question 6. Aqueous ammonia is added drop by drop to a solution of cobalt 2 chloride. Okay, so you remember here they're saying aqueous ammonia, drop by drop until excess. So that means we're going to experience different colors. You guys know cobalt chloride is going to be a pink solution basically if it's in aqueous state. And then when you add dropwise ammonia, when you add ammonia dropwise, a deprotonation reaction occurs, producing a blue precipitate. And this blue precipitate, if you add aqueous ammonia in excess, you're going to produce a yellow-brown solution. And I extracted this from your textbook. Here, this is where the reactions between cobalt and ammonia are shown in your textbook. So the answer here should be D. I will go straight to question 7. Question 7 says, some nickel complex ions are formed by the addition of complexing agents to nickel ion. So here we see, of course, this hexa aqua in aqueous solution. On formation, which of these leads to the most positive increase in delta S of solution? If there is going to be a greater increase, there should be the greatest change in the components. That maybe there are more product components than they were in the reactant side. The difference between the components among the reactant and the components among the products, if it's great, then it means there is more change in. Also, if it's increasing, in this case, you have 2 moles of reactant giving you 7 moles of the product, it means there is a greater disorder that is being created, and therefore there is increase in entropy of the system. So when we use this one here, it's going to be, okay, we go to the hexaaqua of nickel. And this will react, of course, with 4 chloride, because we just need only 4 chloride ligands, producing nickel Cl4, and then 2 plus, here we have 6 waters. Good. Here we have 5 this side, and we have 7 the other side. The difference is just 2. For the other, let me see. For this one here, let's see, Ni, it will be NiH2O, 6. This is 2 plus. Plus, since we have 2, it's going to be 2C, 2O4, giving us, this is going to be 2 minus, of course, giving us Ni, C2O4, 2, that, plus 6 water. So again, here we have 7 and 3. So here we have, let me see, we have 3 on this side, and the other side we have 7. So the difference is just going to be about 4. In this case, actually, B comes out as the best answer because it's giving a bigger change, or it creates greater disorder. So there is more increase in entropy. Question 8. Which of the following is not true of the reactions occurring in the catalytic converter fitted to a car exhaust? The reason as to why they use a catalytic converter is we want to avoid creation of toxic gases, toxic gases actually being released to the environment. So in this case, usually the major reaction occurring is that where the oxides of carbon, give me a minute, yeah, these two, this could be converted to carbon dioxide and nitrogen. Again, this equation is not balanced, but at least instead of releasing carbon monoxide, you end up releasing carbon dioxide, and instead of releasing the oxides of nitrogen, you end up releasing just pure nitrogen. So in a catalytic converter, nitrogen is produced, carbon dioxide is produced. These are safer for the environment than production of carbon monoxide, which can poison people, or oxides of nitrogen, which can be toxic actually, as well as leading to acid rain. So here, which one is most fair? They say they are involved in they involve heterogeneous catalysts. This is correct, because the catalyst used a solid and the reactants are going to be gaseous, so that is a heterogeneous reaction. The carbon monoxide is absorbed onto the surface of the catalyst. That is correct, because it's a heterogeneous reaction as well. And then nitrogen is dissolved from the surface of the catalyst. Of course, nitrogen is a product, so it's going to be dissolved after the reaction has occurred. And then the product causes no harm to the environment. This is wrong because there is some carbon dioxide produced, and this is not necessarily free. It can cause some problems. Question 9 says, the reaction of ethane dioate ions with manganate, this is manganate 7 ions, in acidic solution involves autocatalysis. The catalyst in this reaction is the product manganese. You guys remember from your textbook, we have this reaction like that goes like that. This stage here is when the manganese is really little. However, as soon as enough manganese 2 has been, I meant here the manganese 2 is less, but as soon as enough manganese 2 has been produced, it catalyzes the reaction, leading to the curve going like that. This is a curve showing autocatalysis, so the answer here should be C, meaning manganese 2 is the catalyst in this reaction. Question 10 says, iodide ions are oxidized by peroxidized sulfate as 6 ions. Which of the following statements is true of this reaction? Both ion 2 and ion 3 catalyze the reaction. This is simple. This equation is really simple. The key thing, you have it in your textbook. The reason as to why we use the ion 2 or ion 3, it's because both reactants are negative, and actually they're going to repel each other, making the reaction to be extremely slow. So to increase the reaction, we use the rate of reaction, we use the catalyst, which is going to be able to interact with the two. If ion 3 is used as a catalyst, it's going to react with iodide converting it to iodine and producing iron 2. Then iron 2 will react with the peroxide disulfide, converting it to sulfate, as well as regenerating the catalyst, which is iron 3. Or if we started off with iron 2 as the catalyst, it will react with the peroxide disulfide, producing iron 3, and here we have sulfate, and then the iron 3 will react with the iodide, producing iodine, and then regenerating the catalyst, which is iron 2. So here the correct answer should be A. Question 11 says, which of these could not be formed when excess benzene is heated with trichloromethane in the presence of aluminium chloride catalyst? This is good. So the key thing for us to know is this is what is going to be used to produce the electrophile in the presence of aluminium chloride halogen carrier. So we will produce CHCl2 plus of course AlCl4 minus. This is the electrophile that is going to be produced, and that will attack benzene, producing something like this. The carbon is going to be directly attached to benzene, H, a Cl here, and a Cl here. That is the first product. So this one here, correct, it will be formed. Now the next product is going to be when this actually is going to react with AlCl3 to give us another halogen carrier. Remember we have excess, to give us another electrophile. Remember we have excess benzene. So the second electrophile is going to be generated like that. We will have C, the H is going to be there, one Cl there, but the other is going to be gone, plus Al, Cl4 minus. Now this is going to react with a new benzene. So we will have a new benzene connected to it's connected to that, producing, this is to the carbon, and then there is a hydrogen there. So there is a chlorine, and then the benzene. Basically, I'm drawing this, so benzene will connect here like that. This is the benzene, and that is the previous thing we had previously. Let me take it away. Now this is product number 2, which is basically that. Let's see if we have a third product. A third product will be when this, let me take away the other things so that you can see clearly when I draw the next one. I don't want to use a lot of time. I'm going to cut away this. So this is going to interact with AlCl3, producing AlCl4 minus, and the next electrophile, which is going to be ring, the benzene, that to carbon, hydrogen, and then this is going to be positive, and another ring like that. And then this is going to, later on, it will connect to another benzene, producing something like that, which is going to be this. This will never be produced. This one here will never be produced because there are no other halogens to be removed. There were only 3 halogens, so it's going to be only 3 specific electrophilic reactions that will occur, or 3 specific, basically reactions that are going to occur between the 2. Only 3 products are going to be produced, that, and that. This cannot be produced, so we can end it to that. So this is, I did some explanation for you here. If you want, you can look further to be able to understand. Question 12. What is the molar mass in gram per mole of the organic product when phenol reacts with excess bromine water? If phenol is to react with excess bromine water, since phenol is basically, it has OH, and OH is an electron donating group, we expect substitution reactions to occur at this carbon, that carbon, and that carbon, meaning we are going to have a 2,4,6 tribromophenol, and if you add everything up, you will get a molar mass of 330.7. I'll go to question 13. Which sequence shows these compounds in order of decreasing basicity? Decreasing basicity means from the strongest base to the weakest base. Now, from your notes, you remember we actually said alkyl amines are going to be stronger bases, and their basicity increases with increasing inductive effect. That is one. So also, we also know that the ammonia is going to be kind of a weaker base in comparison to the other alkyl amines. And then in this case, we know that phenylamine is going to be weaker. The reason for that is phenylamine is like that. It has an H2 here. There is a lone pair here that is going to be incorporated into the ring. The ability of amine compounds to be able to act as bases is because they can donate the lone pair of electrons. However, in the phenylamine compound, the lone pair is kind of incorporated into the ring and is not readily available to be used or to be donated in acid-base reactions. So it is going to be the weakest, as you can see. So C is going to be the answer, the alkyl, ammonia, and then the phenylamine. I will go to question 14. Which amine could not be prepared by a reduction of nitriles? To be able to answer this question, you need to know that a nitrile is that. The functional group is a carbon bonded to 4 bonds and then a nitrogen bonded to 1. So it means to be able to have produced, to produce an amine, we should have had a nitrile. So let's see. If this was a nitrile, it would have been a nitrogen here, a carbon, carbon, and this could have been a triple bond. It is possible if this was a nitrile to produce an amine because there is no other bond onto carbon, so it's possible to form that. Now we have to see also this would have been a nitrogen. Let me actually use the examples I used here so that you guys can see them clearly. Okay, got that out as well. Look at this. If this, I will use again a highlighter here. Sorry. If this is the amine, this must have been, of course, the nitrile. It means this should be the nitrogen to represent that carbon to represent that carbon, this carbon for that carbon, and that carbon for that and that. So it means there must have been a triple bond here for us to produce this amine. And if you look at the bonding around carbon, it allows for 3 bonds to exist here. And therefore, when those 3 bonds are reduced in the presence of this reducing agent, we can be able to produce this. So this is also possible. Now let's go to C. For C, we have to look at a structure the way it is. We are looking at producing this by a reduction of this. Now keep in mind, this already has, the carbon here already has that bond, and that bond. It means if this was a nitrile, the carbon, this carbon here, let me use a pen, you can see, this carbon here would have had 5 bonds, which is not possible, and therefore this is not possible. It's not possible that was the nitrile that was reduced basically. This other one, let us see, it's here. If you look at here, carbon is only bonded to 1 bond the other side, so there is a possibility of 3 bonds to exist here, so this is also possible. The only impossible answer would be B, so that's B. We go to question 15. It says, how many different amino acids acids form the repeat units of the polymer shown? So for me, what I did here, I tried to observe where the bonds are, where the connection between the amine part of one amino acid and the carboxylic part of the other. So we have a connection here. There is another connection here. There is another connection there. Another connection here, another connection there. So we have 6 amino acids. However, we gotta know if they are different or similar. I actually observed that this amino acid is similar to that, and that amino acid is similar to this, yet this and that are different. So we have 4 different amino acids. The answer here is gonna be B. Question 16 says, Grignard's reagents reacts with. Of course, Grignard's reagent, these are the reaction I summarized them in here. When it reacts with methanol, it produces primary alcohol. Reaction with aldehydes produces other aldehydes. Basically, it produces secondary alcohols. And if it reacts with all ketones, it produces only tertiary alcohols. And finally, when it reacts with carbon dioxide, it produces carboxylic acid. So this is the only correct answer. These all are wrong. The final question for section A is, the melting temperature is determined for impure crystals of an organic compound. When compared with the data book value for the pure compound, the measured melting temperature is? The measured melting temperature should be lower than the true value, because remember, impurities lower the melting temperature and impurities increase the boiling temperature. So here should be a C. So thank you so much for being with us for this section A for the October 2021. Unit 5 for the Unit 5 Edexcel paper for chemistry. Of course, this is A2 chemistry. We'll see you again when we discuss Section B as well as Section C in the next video.